Yeah, thank you, Christos. So the first talk in the session is by Benjamin Pose from the CA in France, and the title is The Multi-Channel Maximum Likelihood MCMC Method, Extension to Multi-Source Estimation and Evaluation.
Hi everyone, thanks to you all to be here, and I will present to you my work on the extension to the multi-source estimation of the multi-channel maximum likelihood methods. So let's begin with a little introduction on the infrasound technology. So the infrasound monitoring system is designed to detect an explosion of 1 kiloton equivalent TNT everywhere at any time on the globe. Today, 90% of these systems is operational. We can highlight the new station I-16 in China that is certified. And all these stations will detect a wide range of natural and anthropogenic sources like volcanoes, storms, explosions. And that's why detecting explosions in all these different sources with low SNR can be really challenging. We need, of course, some developments for the signal processing. For example, we have the HEF detector that is commonly used in numerous NDC. However, it's principally used in a single frequency band way, and because we have a large variety of signals covering a wide frequency band, we developed at CA the progressive multi-channel correlation in '95. It's a detector based on the correlation, and the main things of PMCC is that we have a time frequency domain, as you can see in this picture. So this picture is from the DTK GPMCC view. So if you want to know more about all the DTK tools, you can come visit the stand of DTK. And here you have the example of a fireball above Japan that was detected last August by I-30 Japan. And what we can see here is the time frequency domain. And you have for each pixel of color the parameters of the azimuth or the velocity. And here you can see in blue, for example, the detection of this fireball. And so PMCC is used operationally since the 2000s at the IDC and is distributed to all the different NDC partners. However, we have some feedbacks when we have unfavorable observation conditions like low signal-to-noise ratio or interfering sources. We have a loss of detection and errors on estimations. That's why we developed a new a new signal processing method, the multi-channel maximum likelihood, based mainly on the likelihood methods. So for the detection, we are based on the generalized likelihood ratio, the GLR, and this GLR has a p-value detection threshold. This is a key point because it's a statistic threshold, whereas for PMCC with the consistence, we have an experimental threshold based on the experience of the analysis. And then for the estimation, we will maximize the likelihood of the maximum likelihood estimator. So we have the theta v, the azimuth and the velocity, the signal power, and the noise power. And thanks to all this calculation, we are able to calculate and estimate the SNR of the signal of interest, but also the uncertainty of the estimations. For example, as you can see on the equation, we have some variables that will control the uncertainty. The M is the number of sensors, the SNR, the frequency bandwidth, and also the time. The time window, the time window length. Here we have some examples on a data set of the station I-37 in Norway. We have at the top the example of the Ugatunga eruption, and what we can see here is the same things and is PMCC, so we have the time frequency domain, and in color we have with the azimuth, and what we can detect with PMCC and MCML is the direct arrivals and also the antipodal arrivals from the opposite point of the Ugatunga point on the globe. And we are able to detect with more detection with PMCC, the secondary waves interacting with the microbaromes at the station. And on a larger data set at the bottom, we can see the difference of detection between PMCC and MCML from 2023 to 2025. And what we can see is that we have almost 3 times more detection with MCML than with PMCC. And we are able to also detect and reveal the seasonal variation of the stratospheric guides. We can see that when there is no downwind toward the station, we are able to detect the microbaromes with MCML, whereas it's not the case for PMCC. And we are also able to detect these microbaromes at around 300 degrees, but also around 25 degrees. So we are able to detect when there is a low SNR conditions and when we are interfering signal of interest. So just a quick conclusion on MCML. MCML outperforms PMCC under unfavorable recording conditions. So when there is SOE interferences or low SNR, when there is a high SNR, it's important to say that PMCC and MCML have similar results. MCML is now optimized for real-time processing and will be implemented in DTK tools in the same time frequency space also. However, these 2 detectors assumes an hypothesis, a single source hypothesis, and as we can see in the examples, it is not valid in reality because we have secondary arrivals from the Ugatunga, but also the microbaromes, so it doesn't hold. So we have to, we want to try to detect several sources at the same time and at the same frequency. Several multi-source algorithms exist today, for example, music or clean, but it's not implemented for real-time processing yet, and we want to have a real-time processing for the mission. So we want to develop and evaluate a multi-source estimators and compare it to the state of art. So to begin with the development on the MCML-based methods, just a quick reminder of the equation of the recording at a sensor. It's when you have multiple sources, it's simply a sum of different signals of interest plus an additive noise that we assume a wide Gaussian noise. One naive method is to use a 2D peak finder on a monosource likelihood. So it's a really naive approach. Another approach is to stay in a monosource hypothesis all the time by subtracting the signals and iterate each time we want another sources. And it can be done because each time we are estimating the azimuth and the velocity, we can then realign all the signals and then subtract it by a certain percentage, here 25%. And then iterate. And here you have an illustration on synthetic signals. We have the likelihood function in function of the azimuth and the velocity. We have 3 sources. You can see it because it's yellow. And the red dots indicates the maximum. And then by all the iteration, we are able to subtract the right signals and then to estimate further sources. Final development is on the frequency component. So we have, as in time, the spectral matrix model in function of the steering vector and the power of the noise and the power of the signals. We can generalize it to the multi-source, and then, thanks to the Whittle likelihood as an estimator, we can iterate to find another azimuth and velocity sources. We implemented it rawly or with an approximation in order to reduce the computational cost. The protocol.
Sorry to interrupt. If you could conclude within 2 minutes, so that we allow some time for questions, you think?
Yes, I'm almost finished.
Thank you.
We have some protocols about the. I will be quick. We have several sources, different frequency bands, different geometries, and SNR. And for the results, we can say that the MLE with signal deflation has the lower fast estimation rate. We have a lower fast estimation rate with a higher number of sensors or with a higher frequency band. Here we can say that music struggles with poor number of sensors. And finally, just to conclude before the conclusion, we have an event of interest. So we have PMCC and MCML, and then with these new methods, we are able to detect all the sources, the microbaromes, the Atlantic microbaromes, the Indian microbaromes, behind the main meteor, the fragmentation of a meteor here, recorded at the I-90 infrasound station at Djibouti. So in conclusion, MCML outperforms PMCC, especially at low SNR and when there is multiple interfering signal of interest. But it's currently undergoing tests at the French NDC and will be implemented in the DTK tools soon, and in the 1 or 2 years, becoming the new operational detectors. This improvement leads to the development of multi-source estimators, and the MCML with iterative signal deflation offers a cost-effective solution. Now for the perspective, we want to try to optimize the percentage of signal of interest that we want to subtract, and then do more systematic evaluations on different events of reference. And finally, we need a more robust cross-processing methods in order to build the events. Thank you.
Thank you. So I see Ron has taken all the praise and disappeared, so I'll take over from here. We have time for one question, but it may be that one of the speakers is not here, so we may have more time for questions later. But we have time for a question now. If there is any question from the audience. Or maybe I can ask a question. Do you think that this method could be also generalized to maybe seismic arrays?
In MCML? Or,
Yes.
Yeah,
MCML.
MCML is currently under test on infrasound data, but we also done some processing on seismic data, and we can say that on the several examples that we use, we are able, for example, to estimate the coda waves after the main seismic arrivals that we don't always have with PMCC, for example.
Thank you. Yes, please, go ahead.
Thank you for the good presentation. I'm wondering if you had a chance to compare MCML method with FK method. Thank you.
Okay. Yes, in fact, the FK methods is beamforming methods like MCML. So I think it would be quite similar, in fact, because it's mainly based on statistics and likelihood. But here, the main power of MCML is that it's implemented in the time frequency domain as PMCC, not as the F detectors that is maybe in the single frequency band. So here the main improvement is that we have this kind of pictures. We can make more observation, more statistics on the different pixels on different frequency bands. But I think the FK is almost used, often used in a 1 single frequency band. So I think the result in 1 frequency band is equivalent. I didn't make the test, but I think it's maybe quite similar. We have to do the test, but we have to have the same time frequency space between PMCC and MCMS. That's why we have this kind of result, and we didn't compare to the FK at that time.
Thank you very much. So we can now proceed to thank the speaker again.